Well, thank you so much for the introduction. Very happy to be the first one. I'm going to say something crazy. Just kidding. So, hi everyone. My name is Zhanzhao. I'm currently a PhD candidate from the Department of Civil and Environmental Engineering from Penn State. And it's my great pleasure to welcome you for this presentation about knowledge-informed machine learning for concrete property prediction. So this work is the outcome from a collaborative effort, and we would really like to thank you for the opportunity to share our research. So machine learning, artificial intelligence, fancy. But are there any challenges associated with this? Can we further improve this? And given that we have a lot of domain knowledge accumulated over the past few decades, can we further integrate them into machine learning models to improve their applications for concrete property prediction? So this talk would be really focusing on addressing those questions. Concrete is the most commonly used man-made materials in the world. Buildings, bridges, roads, dams, and many common infrastructure elements are primarily made of concrete. However, it's a complicated material. It has a lot of components, including cement, water, aggregates, a mixture, etc., which yields multiple phases such as gas phases, solid phases, and liquid phases. And there have been a lot of research efforts in understanding the underlying behavior of concrete materials. So traditionally, the study of concrete materials has relied on experimental methods to establish or analyze the relationship between composition and property. And however, these approaches would comes with a lot of challenges. For example, there could be virtually infinite combination of those constituents, which lead to a very large searching space for concrete materials discovery. And secondly, the chemical and physical properties of those constituents are also highly variable and highly dependent on local resources. So such wide variability would give a lot of challenges in predicting the accurate concrete properties. So this underscores the present need for an accurate and robust model that can enable high throughput mixture design and as well as reducing the labors and computational costs. So recent advances in data-driven techniques, including machine learning, has emerged as a promising solution to those challenges. So without explicit human instruction, machine learning can show its unique ability to mining the hidden patterns from data and learn those relationships and solve the complex tests. So as such, machine learning has been a really good tool to account for the inherent complexity of concrete materials. Nevertheless, machine learning models typically require a massive amount of data. And after our surveys on the current data set in concrete literature, we find that the majority of the data set utilized in literature are pretty much small at scale. So this raises the question or concern about how we can effectively learn from those small data sets and how we can generalize the model outside the training domain. So we propose a framework called knowledge-informed machine learning, essentially to integrate domain knowledge into machine learning. So how did we do that? So we have historical data, which essentially has the concrete mixture proportion as the input and compressive strength as the output or other concrete properties. And we also have domain knowledge accumulated over the past few decades and condensed into empirical and physical models. So with the input from the historical data, we can put them into the empirical and physical models and get the output like simulated concrete compressive strength. So we will be able to combine those knowledge with data together by utilizing the following three methods. Data augmentation. We can essentially append the simulated output as additional data set to increase the data size. And secondly, feature enhancement. We can utilize the simulated output from the physical and empirical models as the additional feature or input variable for machine learning modeling. Thirdly, model pre-training methods. So we can pre-train our model by utilizing the simulated output from the physical and empirical models and fine-tune them with the real and measured values for better performance. So these are the three main methods we are going to present in this presentation. We are going to demonstrate this framework in the context of concrete stress prediction, because this is the most common application of machine learning in concrete research, and concrete stress, by all means, is the very important parameters for construction design. We have laboratory and field data for concrete with approximately about 400 or 1,600 data points respectively. And we also have input, which is essentially the concrete mixture design, such as quantities of cement, fly ash, slag, aggregates, water, and water reducing agents. And the output would be 28-day compressive stress. So the domain knowledge we are going to use, and which are also condensed in empirical models, would be the inverse relationship between water to binder ratio and stress. So we are going to use the two formula as listed here, Abrams formula or power formula, to mimic this behavior. And in terms of the domain knowledge condensed in physical models, we will be using the thermodynamic and multi-scale-based physical modeling, which essentially contain the knowledge related to kinetics, thermodynamics, mechanics for cement hydration, and microstructure development. So we first want to show you the performance across this model. So you may see the y-axis would be testing root mean square error, and this is essentially a metric to a measure for model accuracy performance. And lower the error would be, the higher performance for accuracy for the model. And we first compare the first three models with the colorful color here, and compare with the empirical model for the first two boxes. The physical model which shows a higher error and thus a lower accuracy. This is not surprising because there could be a lot of assumption in the physical models, such as the compositional information and kinetics information about cement, fly ash, and slag, which are all not included in the data set we use. And we highly encourage researchers and engineers to gather this information when you collect data, and which could be very useful for machine learning research. We also compare the baseline performance for the machine learning models, super vector machine, k-nearest neighbor, random forest, and neural network models. And you may find that neural network models would give the lowest root mean square error, and as such the highest accuracy performance. So we selected this to further explore the effect of knowledge integration for our framework. So knowledge integration. Again, the y-axis would be testing root mean square error, and compared to the baseline model, which indicate by the dark markers or the dark dashed line. If you view it vertically, you may find that all these colorful markers representing the knowledge-informed machine learning model, or KIML, they might not give a quite different accuracy difference, or essentially some of them would give a higher error or thus worse accuracy performance. So what's the point for knowledge integration? We further demonstrate potentially one benefit in this figure. That would be the total number of training epochs. If you can view this figure horizontally, you can find that all the colorful markers or the knowledge-informed machine learning model, they can reduce the number of training epochs significantly, which means they can accelerate the training or reducing the training time, which would be very useful. So are there other benefits associated with knowledge integration into machine learning? Yes, there could be more. So, such as smaller sample size required, better extrapolation capacity, or higher robustness to data outlier. And we are going to explain one by one. So first of all, accelerated convergence. As we saw in the previous slide, by integrating knowledge, it can reduce the total number of convergence. And we also want to visualize this in the form of training curve, essentially mean square error as a function of training epochs or training iterations. So you can find there are two types of curve, like the colorful solid line here or the colorful dashed line here. They can really reduce the mean square error at a given training epoch compared to the baseline model, which is here. It might not be really visible, but they are on the top right-hand side. So this is very useful when we want to scale our model to a larger one or use for few applications. Secondly, smaller sample size required. So as mentioned, in quantity literature, there might not be that much data available for machine learning research. So we might have concern about this, but how important data availability will be. So we reduce our training sample size from 100% to like 10%. And you can see for the baseline model, it can really, for the baseline model with gray color, it can really reduce the accuracy error, with still the accuracy performance, or increase the error values. So this tells us that limited sample size can be a concern. And either we have to increase the sample size, or we have to do something to avoid this issue. So you can see by doing data augmentation indicated by the figure on the left-hand side, or model pre-training, they can both reduce the mean square error and thus increase the accuracy performance by when we have a smaller sample size. And you might notice at 100% training sample size, the data augmentation methods might give a higher error. This could be due to the fact that we are augmenting the data set with some simulated data points, which obviously are not as accurate as the real and measured data points. So this would introduce some bias and thus lower the accuracy performance. So thirdly, better extrapolation capacity. And so you might be aware of the fact that a lot of concrete literature might develop models based on data in the laboratory and predict again in the laboratory data set. But as an engineer, in practice or in the field, they might want to use for field concrete prediction. So if we directly utilize the model built on laboratory data and predict on field data, would that be a concern? Yes, might be. So the reason could be twofold. We might have a high variability in terms of the input space. So here we condense the 7 input variables into 2 dimensions, trying to show how the difference of the distribution from those data would be. And you can see that field data would really give a larger, wider distribution compared to the laboratory data. And secondly, compared to the control environment in laboratory, field concrete would experience a more high variability due to the varying temperature and humidity. And also the measurement of compressive stress, etc., can also influence by human operation. So that would also give us another uncertainty for the output space, meaning the concrete property data, or here, concrete compressive stress. So these two would raise a concern about directly applying machine learning model developed on laboratory data to field data. So we want to see how effective our framework would be when we do these things. So all the data points showing here would be related to directly using the models built on laboratory data and then apply on field data. So compare with the baseline model indicated by the gray box, there are 2 methods, namely data augmentation and model pre-training, can really reduce the error and thus improve the accuracy performance. And we also want to know that the model that built on laboratory data and predict on laboratory data, which yields a mean square error about 5 megapascal. Compared to that one, the one that directly apply on field data would really increase the error and thus lower the accuracy. So this also confirms our concern about extrapolating our model from laboratory to field data. Last but not least, higher robustness to data outliers. So when we collect data from experiments or from literature, we might mistakenly enter some wrong number in the data sheet. So that's how we might encounter outliers in our data sheet. So we want to see how sensitive of our proposed method to those outlier portions. We vary the outlier portion from 0 to 5%, and you can see that for the baseline model, it is very sensitive to data outliers. But if we do some knowledge integration like data augmentation, it can really reduce the error across the range of outlier portions and improve the accuracy and thus the higher robustness to data outliers. Awesome. So in summary, we show that the proposed knowledge-informed machine learning model can really allow faster convergence, require smaller sample size for training, and ensure better generalizability, performance in terms of extrapolation and robustness to outliers. And we want to highlight that the methods we are using here are really easy to implement and could be very effective, as you can see just now. And this could be very beneficial when we apply those machine learning models in the field. So while this framework is showcased in the context of concrete property prediction, we want to highlight that this can be easily extended to predicting other properties of concrete materials or other composite materials. So with that, thank you very much for your attention. I will be more than happy to answer any questions.